Hi everyone, today we're telling you about our plan to apply additive manufacturing techniques to dental implants.
Have you ever thought about how important your smile can be in everyday life? What if that smile is missing a few teeth? Well, for our clients, those who are missing a tooth, dental implants are a very important part of their lives. Tooth loss is a fairly common problem with patients experiencing this due to gum disease, tooth decay, a failed root canal, or an accident. Therefore, our clients, people with tooth loss, rely very heavily on dental implants as it is the most common form of therapy for the loss of a tooth.
Losing a tooth may not seem like a big deal at first, but if you leave it untreated, it can cause a domino effect of increasingly severe problems. For example, it can cause malocclusions or the crowding of your teeth, like you can see in the GIF here. And then this can lead to shifting of the gums and deterioration that leaves wounds susceptible to infection and the deterioration of the bone and the eventual loss of functions. Dental implants are a good replacement option for this because they interface with the bone as well and restore root function and not just the crown.
So in restoring the functions of the root and the crown, current dental implants aim to, one, accomplish this by using a material that can withstand the forces exerted on the teeth and jaw during daily life. They also work to optimize wound healing, which is an important process during when there's an implant added to a body. And then also finally integrating the implant into the surrounding tissues is important to provide long-lasting stability and success in the implant. So currently there's a variety of dental implants on the market. There's a focus on the dental implant screw specifically, because that's what interfaces with the body and that's what we're focusing on as well. Most often these implants are made of titanium or zirconia, which has high strength and biocompatibility. On the right, you can see images from two different titanium implant designs from the companies of Straumann and Noble Biocare, which are major dental implant companies. These designs have very different screw designs, surfaces, and material characteristics, all with the goal to promote wound healing and osseointegration. However, there's still some current issues with these kinds of implants. For one, peri-implantitis or inflammation of the tissues surrounding the implant can cause bone and mucus damage. Implants can also fracture or loosen over time, which is a result of poor osseointegration. So the goal of our project was to improve on these current issues.
So to summarize, the key functional specifications of our design are that it should promote osseointegration into the surrounding bone tissue, as well as interface comfortably with the gum and not cause any slipping, irritation. And it should also be able to withstand the natural mechanical forces applied to teeth during mastication without cracking, slipping, or loosening. And so to put these specifications into numbers, like we have here, it should be able to withstand essentially the natural forces and environment of your natural teeth. And so that means withstanding these stress strains and surviving cyclic loading, as well as being able to be manufactured to the following lengths and diameters so that it can fit any of the teeth in the mouth.
The current issues with the cold standard titanium alloy dental implants include mechanical deformation, crack propagation, and reduced osseointegration, leading to dislocation of a screw. These issues contribute to over 500,000 dental implants failing each year in the United States. To address this problem, our group proposes to utilize additive manufacturing to produce Inconel 718 dental implants. Inconel 718 has various mechanical properties. As of now, Inconel 718 is a nickel alloy used in the aerospace and defense sector to produce jet engines, spacecraft. However, our group proposes to introduce it to the medical device sector. The biocompatibility enhancements, such as the addition of a peptide coating, will promote osseointegration of the bioactive protein marker as well. Through additive manufacturing, one can also control the amount of porosity of the device. To promote osseointegration, the device will be modeled to be 10% porous to allow for osteoblasts to diffuse. It should also function like a tooth, which will be modeled through the metal 3D printing through individual designs. Our group has decided to utilize Inconel 718 because of the gold standard, as its mechanical properties improve upon the current device and promote increased osseointegration. Inconel 718 has a higher compressive strength than the current gold standard, with a strength of 1.5 megapascals compared to 0.8 megapascals. Compression of the device is one of its main functions, as chewing provides great compressive force. Currently, the main mechanisms of dental crack propagation is due to mastication. So if one can increase the compressive and yield strength of the device, the rate of crack propagation in the implant should decrease. One example of an improved mechanical property in our device is the increased hardness of Inconel 718, resulting in reduced wear of the dental implant. Wear of metal implants is a major concern, as degradation of the implant can lead to corrosion and increased risk of screw dislocation. Increased flexural rigidity of the device will reduce the bending of the screw, which is a major factor in screw dislocation and integration with the alveolar bone. One of the major concerns with any implant is its ability to integrate with the body. In order to function, our dental screws must integrate with the alveolar bone, similar to the way teeth do. To promote osseointegration, our team will use the design capabilities of 3D modeling to design 3 porous implants similar to the pictures shown in the slide. Inconel 718 is incredibly anti-corrosive and will serve its purpose inside the body. Finally, the peptide coating will increase the rate of native cells to adhere to the implant, improving the overall anchorage of the screw to the alveolar bone.
And also, as discussed briefly earlier, peri-implantitis is a major issue with current dental implants. It's often caused by bacteria that enter the implant tissue interface due to a lack of integration between these two materials. Recent studies have shown that peptide coating can help improve cell growth on implant surfaces. More specifically, the LAM and AMBN peptides have been shown to increase interactions of laminin and amyloidoblastin with implant surfaces. This also increased epithelial cell migration and adhesion to implants. So we propose that we will also use this combination of peptides in our implant to improve the attachment of soft tissue to the Inconel implant material and reduce the impacts of peri-implantitis in our implant.
So to go into more detail about our fabrication processes, a big part of our design is the additive manufacturing of our Inconel 718 screw. And this is more specifically with powder bed fusion, and this is a type of additive manufacturing in which layers of the material powder is deposited and then fused together with a laser heat source. And the advantages of this over other types of additive manufacturing or even other types of 3D printing are that it will allow us to conserve material, print at higher resolutions, and allow us to customize the screws per batch. For our protein coating, in order to effectively coat this device, we have to first prepare the screw by activating the surface with the oxygen plasma cleaning, and then salinization, which is the process of coating a mineral surface with or organic functional molecules. And this can be done to change the surface qualities of metals in many different ways, but for our purposes, we would help to improve the substrate binding and help the peptide coating immobilize further so that it can withstand the mechanical corrosion. For our sterilization of our design, we decided to go with dry heat sterilization in a hot air convection oven at 160 Celsius for 2 hours. That's the standard. And the advantages of this method of sterilization over others are that it can effectively clean porous surfaces, which can be difficult with chemicals, and it is also minimally corrosive. It's also a lot cheaper than other methods and doesn't require very specialized equipment.
test the mechanical properties of our dental implant, we would perform two different tests. The first is a yield strength test, and you can see the setup in the figure here. In this test, a dental implant is loaded into a test fixture that holds it at an angle relative to the loading device, which in this case was 30 degrees. Then the loading device applies a force at this prescribed angle until failure is reached. Using this collected data, we would be able to compare the yield strength of our dental implant to those that are already on the market, which would help us to prove our safety and our efficacy. The next test that we would perform is a corrosion and fatigue strength test. This is the potential setup in the next slide. The potential setup is shown for the dental implant using a testing chamber that simulates a corrosive environment inside the human body using a saline solution. Then the implant is tested for fatigue strength using an axially loaded test rig, which is what you see in the diagram. This would determine that Inconel 718 can be safely used in the human body without the risk of corrosion. Next, we would test for osseointegration, stability, and wound healing. Some of these tests that we could do include a histomorphometric analysis, a push-out pull-out test, and an insert removal torque analysis. A histomorphometric analysis is obtained by calculating the peri-implant bone quality and bone implant contact from a dyed part of the implant and the peri-implant bone. This is used for short-term experiments and non-clinical studies, so that would be used for our initial testing and prototyping of the implant. The push-out pull-out tests are done by applying a parallel load to the implant bone's interface and then measuring the interfacial shear strength, which you can see in this diagram. This test is used to analyze the wound healing at the site where the implant makes contact with the bone. Finally, we would use an insert removal torque analysis, which is also shown in the diagram. This test is performed by applying a torque onto the implant, and then the implant is considered stable if the reverse torque is greater than some predetermined value that we would set. All of these tests measure the stability of the insert, which in turn helps to assess the osseointegration, because if the implant is not stable, then it is not properly anchored and osseointegrated with the bone. Some of our standards that we would use for the functional test would be the ISO standard 14801 for the dynamic testing of a single post endosseous dental implant, and the ASTM standard F1801, which is the standard practice for corrosion fatigue testing of metallic implant materials. The ISO standard is generally used to compare the different sizes or designs of dental implants. So these testing conditions would be used to compare our dental implants with the current standards. The ASTM standard describes the procedure for performing corrosion fatigue tests to obtain the SN, or stress cycle fatigue curves, statistically derived fatigue strength values, or both for metallic implant materials. Then to test for biocompatibility and cytotoxicity of our implant, we would follow the ASTM standard F748 for testing biological test methods for materials and devices. According to that standard, we should perform the test of all of the following that are listed here.
As with any device, there are certain costs and benefits that should be observed. For example, the cost of our device include the surface finish. Through additive manufacturing, it may not have as inherently natural surface finish compared to traditional manufacturing techniques, so we would most likely need to do post-processing. Additionally, the titanium standard is more inherently biocompatible. However, through the addition of the peptide coating and porosity adjustments, we hope to be able to combat that as well. The upfront cost of installing a metal 3D printer may be high. However, using Inconel powder is significantly less expensive than titanium alloy powder, which is $500 per kilogram versus the $80 for Inconel powder. There are certain benefits as well. Using the additive manufacturing techniques, you can minimize waste, have custom individual designs, and are flexible that can be made through techniques that are not through traditional manufacturing methods. Thank you for your time.
All right, that was 14 minutes.